Hey everybody, Jake here coming at you with another math lesson today, doing it live again this week. Hope everybody's having a good start to your week. Just doing our weekly Monday night live stream. This week we're going to be talking about some local minimum and maximum stuff and also absolute or global minimum and maximum. We're going to be talking about kind of the difference between those two things, how to actually find critical numbers. And then we do also have an example that we're going to be going through about sketching a function based on local and absolute maximum and minimum values that are given to you. So a few different interesting types of examples here, all having to do with relative and absolute extrema or extreme values and kind of what that all means. So let's just go ahead and jump on into the first problem we have here. This is actually a problem that came out of a textbook. But I think it's just a good kind of starting place when you're talking about, local versus absolute maximum and minimum values. So first thing we're going to do, explain the difference between an absolute minimum and a local minimum. So in general, just one quick thing I want to point out. Whenever you're dealing with an absolute minimum or maximum, absolute is also kind of interchanged with the word global. So global and absolute minimum and maximum are the exact same thing. And then similarly, the word local is often interchanged with relative. So a local minimum or maximum is the same as a relative local, or a relative minimum or maximum. I'm sorry. So either way, these two things are two different concepts within the realm of extreme values. So I wanted to just kind of touch on the difference between those two things. So really, there's kind of, they can be summed up pretty simply just using English, just using words, where basically an absolute minimum or maximum is essentially just the absolute highest or lowest number that a function takes on within a certain domain. So the total, basically it's higher or lower depending on if you're looking at a maximum or a minimum. In this case, we're looking at a minimum. So basically the absolute minimum is going to be essentially just the point on your function that is lower than all the other points. On the function. And the kind of main difference there, as opposed to what a local minimum is the local minimum is going to be basically the point that is lower than the points around it on F. So lower than basically the points within the little neighborhood around that area. So lower than basically nearby points on F. So absolute is lower than all the other ones, and local is just lower than all the points that are really close in that area. So let's kind of just think about what this actually means from a mathematical perspective. And actually, before I get into that, there is one quick kind of thing I want to point out with absolute. Absolute, typically, you're going to be looking at the absolute maximum or minimum value within a certain domain. So absolute is typically just going to be on a certain domain, which typically is going to be given, right? It's going to say within this certain domain, find the absolute max and min values, or find the absolute max or absolute min within a specific domain, where local doesn't really care about domain because you're really just looking at points really close to the point you're looking at. So that's one other kind of main difference is whenever you have a problem dealing with absolute max or min values, typically they give you a domain, where with local, they typically don't. Okay, so let's think about from an actual mathematical perspective what the difference between these two things are. Essentially just looking at like the definition of a absolute minimum versus a local minimum. So basically with an absolute minimum, we have basically some number that is within a given domain of our function. So we have some number c, really. We're just picking some arbitrary constant to represent this. Some number c, which is in a domain D on our function f. And if we basically plug that c into f, so we get f of c as our output, that is going to be an absolute minimum. So absolute minimum if the value of basically f of c is less than or equal to f of x for all other x's, or I guess I should say for all x's within the domain D. So for all x within the domain D. So this little symbol right here, this little like kind of curvy backwards capital E, that just means x that is an element of D. So that just means basically for all x values within our domain of this domain D here, if plugging in C, plugging in some number, some specific number into our function f gives us a smaller number than any other point, plugging any other x value into our function, then we know it's an absolute minimum. So that's just kind of math talk to basically say whatever number we plug into our function f. So if we think about it graphically, if we have some function f where we have this kind of defined domain with edges here and here, whatever point we plug into our function and get the smallest possible output, that is going to be our absolute minimum. So basically this would be like if we imagine like our x-axis up here, for example, if we plug in x equals c, so this is c on our x-axis, this output right here would be f of c. This is going to be the absolute minimum of our function within this domain D. Okay. So then the kind of difference there between that absolute and then local, if we're thinking about a local minimum, in that case, we're just going to say basically for some, again, we have some number c, some unknown number, which is a constant, some number c, which is, defined. It is a part of our function f. It is within the domain of f. We're going to have f of c again be a local minimum if f of c is less than or equal to f of x for x's near. Actually, let me write this out a little bit more expanded. For x is near x equals c. So essentially, like I was kind of saying earlier, the absolute minimum is going to be the point of your function that is lower than all the other points on your function within this domain, where a local minimum is just the point of your function that is lower than the other points around it. So what that means is functions can have many local minimum values, right? So let's say we have a function that looks like this. We're going to have a local minimum right here and a local minimum right here, because in both of these cases, this point right here is lower than all the other points around it, just within this little tiny neighborhood of x values around it. And then same thing here. This point right here is lower than all the other x values in a tiny little area around x equals c. So I know this is kind of like arbitrary, saying that, we just want to look at x values that are near c. And that is true. But really the idea there is you're just looking at x's that are within a tiny little area around your c that you're looking at. And we'll kind of get into how to actually find these, but that's kind of the idea behind absolute versus local minimum or maximum values. Obviously, if you were looking at absolute versus local maximums, you would look at the highest point within the domain, or a point on our function that is higher than the other points within this little neighborhood. In this problem specifically, we are looking for minimums, so we want to look for points that are lower on our function. So that's kind of the main difference there. I'm not seeing any questions in the live chat. As always with these live streams, if you do have any questions along the way, you're welcome to throw them in the live chat, and I'll be happy to address those as we go. And if you are getting some value out of this video, do me a favor and hit that like button down below. It's a huge help to my channel so I can keep making more videos like this, and we can keep crushing it all term long together. All right, so that is it for that first example. Let's go ahead and get into our second example here. We're going to sketch the graph of a function f that is continuous on the closed domain from 1 to 5 and has these given properties. There's going to be 4 properties that we have here. We need an absolute minimum at 1, an absolute maximum at 5, a local maximum at 2, and a local minimum at 4. So the first thing I'm going to do here is just kind of point out, or just highlight, I should say, where we want minimums and maximums. So first of all, we have an absolute minimum at x equals 1. And then we have a local minimum at x equals 4. Okay. And then let's go with, trying to find a kind of different color here. We'll go with this. So we have an absolute maximum at x equals 5 and a local maximum at x equals 2. So let's think about, again, kind of just the differences between a local versus an absolute maximum and minimum. So local means it's just higher or lower than all the other points really close to it. Absolute max or min means it's higher or lower than all the other points within the domain. So in this case, we are given a domain of 1 to 5. So we don't really know anything about exactly the height of this function. We don't have any information on y values of this function. So it's really kind of arbitrary where we want to put our y-axis in relation to our function. So I'm going to go ahead and basically just put the whole function above the x-axis, which again is just kind of an arbitrary decision. But the point here is we do know that we have a specific domain. Our entire function exists between 1 to 5. So between x equals 1 to x equals 5. So if we were to label our x-axis here, 1, 2, 3, 4, 5, we only need to look basically between x equals 1 to x equals 5 to sketch our function out. Now, what we know is that we have an absolute minimum at 1. So basically our function is as low as possible within this domain. So whenever I'm saying in this example as low as possible or as high as possible, I only care about this domain. We're only worried about this domain of 1 to 5. That's the only part we need to kind of worry about at this point. So our function is as low as possible at x equals 1. So basically wherever we want to put this point of our function, let's just say we put it here. This is at x equals 1, y equals 1 maybe. It doesn't really matter what the y is, but the point is the rest of our function all the way for the rest of this domain needs to be above this point because we know that we have an absolute minimum at x equals 1. So basically the rest of our function needs to be up above this kind of red dotted line here based on the fact that our function is going to be going through this point. Okay. Similarly, if we want to look at our absolute maximum, our absolute maximum occurs at x equals 5. So basically at x equals 5, our function is going to be as high as possible. So the rest of our function within this domain from 1 to 5 has to be below this like greenish blue dotted line up here. So basically our entire function needs to exist between this like box, basically. It needs to go through this point here and this point here at these corners of the box. The other piece we need to make sure is that we have a local maximum at 2. So basically we need to have some sort of a curve like this where we kind of are going up toward that point from the left and then going down to the right. So basically we have this little kind of local max, like an N shape, where the top of the N is at x equals 2. So basically at somewhere along this vertical dotted line here, we need a local maximum. but it needs to still be below this line up here. So it doesn't really matter where we put it. We just need it to be below that line and above that line. But what we are going to need to make sure to do is kind of come up from the left over here and then go down to the right over here. Okay. Then we are going to have a local minimum at 4. So similarly, we need to create a local minimum at x equals 4, which is going to be more of like a U shape, where we are kind of coming down from the left, hitting our local minimum at the very bottom of this U, and then going up to the right. So that's going to be at x equals 4. And again, it doesn't really matter where we put this point height-wise. We just need to make sure it's above this dotted line, this red dotted line down here, and below this greenish blue dotted line up here. Now, we also know that this is going to have a local minimum, so we probably also want it to be below this point so that we can kind of come down from over here, curve up somewhere down here. So like down here maybe. We need to come down from the left and then curve up as we go off to the right. So we kind of have this general flow of where our function needs to go, where we're having exact perfect little tops and bottoms at these local maximum and minimum points, and then, you know, kind of reaching a maximum at the right, top right corner, and reaching a minimum at the lower left corner here. So these are really the only 4 pieces of information we have, other than, I guess, the fact that we know we have a function that is continuous throughout this entire domain. So from 1 to 5, we need to have a continuous function. Essentially, we need to be able to draw this whole function from the left edge of this box to the right edge of this box without picking up our pen. So that's really pretty easy to do. We really just need to make a continuous line that connects all the dots that we've gotten here, creating local maximum and minimums where we need it, and then an absolute maximum and minimum where we need it as well. So we have our absolute minimum, our local maximum, our local minimum, and then our absolute maximum, exactly where, you know, we had these properties that told us where those were going to be. Okay. All right, I'm not seeing any questions in the live chat. We'll keep on rolling here. Again, if you're getting some value out of this video, do me a huge favor and hit that like button down below. And if you do want more videos helping you through calc this term, go ahead and hit that subscribe button down there too while you're there. We'll keep on crushing it together all term long. I'll have plenty more videos throughout the term to help you learn all the stuff you need when it comes to calculus. So go ahead and subscribe and hit that bell icon too. All right, and I do have these live streams typically every Monday night. Sometimes I don't if there's a holiday or something like that. But yeah, typically every Monday night, 5 o'clock Pacific time. Be sure to join us for these live streams each week. Any questions you have, whether it's on topic or not, feel free to throw them in the live chat, and I'll do my best to answer them. All right, but let's go ahead and jump into this third example here. We are going to find the critical numbers of the function f of x equals x cubed plus 6x squared minus 15x. So first question here, when you're looking at a problem like this, what is a critical number? How do you find a critical number? Well, a critical number occurs in 2 places. There's really 2 conditions that can be met in order for a specific x value to represent a critical number of a function. 2 things to think about. First of all, a critical number will occur wherever f prime of x equals 0. So in other words, if you take the derivative of your function and set it equal to 0 and solve for x, whatever x value makes this equation be true is going to be a critical number. Okay. The second condition that can create a critical number is wherever f prime of x does not exist. So that's kind of a common one that people miss. Not only can you create a critical number, or I should say find a critical number at a place where the derivative of your function equals 0, but also where your derivative does not exist. So if you have some function where you take the derivative and then there's some x value where that function would not be defined, like for example, if you find a situation where you have a fraction, your derivative is a fraction, and some place where x makes the denominator equal 0, you're dividing by 0, your derivative would not exist there. So that's just one example. There could be other things that could create that. But These two things are what we want to look out for. So in other words, well, I guess not in other words, but the first step when you're trying to find the critical numbers of a function, it's always going to follow the same process, right? So the first step is always going to be find the derivative. Obviously, both of these conditions require us knowing something about the derivative of the function. So you're always going to start by finding the derivative. So let's go ahead and do that first. In this case, this function can be found, the derivative of this function can be found simply by using the power rule. So we can bring our power down in front and then lower our power by 1. So that gives us a 3 down in front, leave our base x as x, and then minus 1 from the power. 3 minus 1 is 2. Okay. The derivative, again, of this term will be found with the power rule. So we can bring our 2 down in front. 6 times 2 is 12. Leave our x as x. Subtract 1 from the power. 2 minus 1 is 1. X to the first power is the same as just x. So I'm not even going to put that there. And then minus the derivative of 15x. The derivative of a constant times x is always just going to be whatever that constant is. So it's going to be minus 15. Okay. So here's f prime of x. Here's our derivative. So let's think about each of these two conditions where critical numbers could arise. First place is going to be where f prime of x equals 0. So if we take our f prime of x and see where it equals 0, that should tell us where our critical numbers are. Okay. The other place would be where f prime of x does not exist. Well, let's look at this function here for a second, because not all functions are going to have x values where the function does not exist. So this may not be applicable, but you always want to consider it just in case. So in this case, we have a polynomial, right? Some coefficient times x to a positive integer power. Some coefficient times x to a positive integer power. Or a constant, like in this case. So all the terms here are basically having the sum or difference of a bunch of terms that kind of have this format where you have a coefficient times x raised up to some positive integer power. That just means a positive whole number is going to be a polynomial. So this is an example of a polynomial. Well, polynomials exist for all x values. That's just kind of a property of polynomials. Therefore, this, in this case, is not going to have any, we're not going to get any x values from this second condition here. F prime of x exists for all x values. There's not going to be any places where this does not exist. So this is really the only thing we need to worry about in this case. Where does f prime of x equal 0? Well, we could figure that out whenever you have a polynomial equaling 0 and you're trying to solve for x. Typically, the best strategy there is going to be to factor out that polynomial. Well, in this case, we can do that. This polynomial is going to factor out, and it's actually going to factor out to 3x minus 3 times x plus 5, right? You really just want to think about kind of what, well, I'm not going to get into kind of the full process of factoring in this video. That would be a topic for another video perhaps, but we can kind of reverse confirm that this works if we think about foiling this out. 3x times x does give us 3x squared, okay? And then 3x times 5 gives us plus 15x, minus 3 times x gives us minus 3x. So 15x minus 3x does give us 12x. And then finally, negative 3 times positive 5 gives us negative 15. So this kind of factored out version is equivalent to this foiled out version. So when you have two factors like this and you know the product of those two factors equals 0, what you can do is split this into two separate equations, because if anything times 0 is 0. So if this piece equals 0, then the product of those two things will also equal 0. Similarly, if this piece alone equals 0, the product of these two things will equal 0, because we'd have some other number times 0. So we can kind of split this into two separate problems. Okay. And then we can solve each of those on their own. So in this case, we can add 3 to both sides. 3x equals 3, divide by 3, x equals 1. And in this case, we just need to minus 5 from both sides, x equals negative 5. So x equals negative 5 and x equals 1 are going to be the two critical numbers of this function that we had up here. So that's it. That's really all you have to do to find critical numbers, is just think about those two conditions. What x values will create the situation where f prime of x equals 0 or f prime of x does not exist, and whatever the list of x values are that create those two situations will be your critical numbers. So in this case, this function has just these two critical numbers. And let's see here, not seeing any questions in the chat. So we'll go ahead and wrap things up there. Again, if you did get some value out of this video, do me a huge favor and hit that like button down below, please. Go ahead and hit that subscribe button while you're down there. And hopefully I'll see you next Monday night for our next live stream. And we'll keep on going through calc topics and learning calculus together for the rest of the term. But we'll go ahead and wrap it up there. So thanks, and see you next time. Have a good rest of your night or day, depending on where you are.